My name is Jeremy Frey. I'm working in the chemistry department at the University of Southampton. I'm going to give you a talk now on solving the world's problems with chemistry, because of course, as a chemist, I believe that we can solve at least some of the world's problems with chemistry. It'd be nice to come and give this lecture in person to lots of you, but actually I can reach a wider audience this way. This talk is normally given by Professor David Reed, but he's not available at the moment. So I will attempt to give as good a talk as he does. So I've changed a little bit of the talks from ones he do to some things that I'm personally working on or know more about. So let's have a look at it. So first of all, one of the most important things, particularly given the COP meeting that's going on at the moment up in Glasgow, under the auspices of the United Nations a few years ago, 2015, the UN developed a series of goals around sustainability for the globe. One clearly is associated directly with climate, and that's what's currently being discussed. But there are many other aspects of life and the globe on the Earth that mean that we should be working not only to sustain the environment, but to provide an environment that is worth living in for as many people as possible in the world. And certainly as a chemist, I consider that chemistry has a lot to add to almost all of these 18 sustainability goals. And some of that I hope will come out in the talk that I'm going to give now. So yes, the big news this week is United Nations COP26. Hopefully the world is going to come to its senses and realize that we need to do something seriously about the environment. We've already had a significant amount of warming since pre-industrial times, and we basically need to ensure that we don't have too much more. The problem is this is not easy. It's not easy because there are many people who still need to increase their energy consumption per head to get to a decent standard of living. And many of us who are used to expending significant amounts of energy and causing climate change issues around the carbon dioxide, which we'll talk about today, and others as well, other problems as well, we may have to change our lifestyles quite significantly to ensure that we can continue to live safely in the world for all of us. So this is not a trivial thing. There have been some good announcements, but I suspect a lot more is really needed to be promised, and a lot more money and time and effort and human ingenuity is going to have to be spent to ensure that the world is livable in 50 years' time. And chemists have a lot to contribute there. Now, just in case you thought that we were, chemists might be running out of things to do, there's a very interesting publication called The Onion, which not entirely all to be believed, I would say, but that we have 118 elements. Along with the physicists, we occasionally make a new element. We're at 118 at the moment, but the suggestion was maybe we should make some more and have more available. In reality, there aren't any more to be made available in the main part of the periodic table, despite this wonderful offer to buy an element. But there are new isotopes and things that could be used. But I don't think you need to worry. There's more than enough chemistry that we can do with the elements that we've got. So chemistry is not running out of things to do anytime soon. Okay, so what I wanted to see is, in terms of this particular really important thing around climate change and what we need to do, I thought we'd see what amongst the audience here, see what your sort of general views are, and as well as see if we can test whether or not this VVOX poll. So I'm going to start the poll. Hopefully some of you got the app working, and we'll see whether or not you can put some answers in here, whether you're a climate change activist. I think if you're an activist, you're probably a believer, but you might be a believer without being too much of an activist. You might be agnostic. Maybe you think that some things are not quite as they seem to be in the media. You might be a skeptic. You might think that actually that there are some serious considerations still. Or you might be like one of the characters here, a non-believer. I think you probably all know which one is the activist and which one is the non-believer. So I understand we have 33 of you have got polls open, and we've got 28, 29. Okay, you're coming in on this here. I've got two screens here because of some problems. So I have to remember which one it is that I have to click to get the responses here. We got some more people coming in. Oh, it looks looking good. Okay, I think we'll close the poll at this time. Other people, if you're not yet on, you can join into later polls, no problem. So I think if I click that, closes the poll, and here we go. Right, so 20% of you, or just over, are activists, 70% of you are believers, and a few are agnostic, which is sensible, and nobody is a non-believer. So I think that's really interesting to see where you are in this debate. I'm not surprised. I think the younger people at the moment are well versed in what's going on, and I think you're thinking about it in a very sensible manner. What we need to give you is the tools to do something about this and help the future. So that's really interesting to see, and thank you for providing that background. Okay, well, for some reason, this poll doesn't seem to be letting me poll you, but this was a previous time when one of the problems we've got here is fossil fuels. Now, fossil fuels have been really important in powering the economy, and that's coal and oil. And we asked a previous audience, how long do you think the oil supplies will last? And quite a few people obviously thought that less than 25 years. And that probably was based on the idea of oil. I have to say that the oil industry has predicted that we will probably run out of oil in 25 years every time in the last 25 years. Some a bit longer, and I think that maybe you're taking into account the fact that coal reserves are in principle much longer lived, and there are far more coal. But we'll see there are real problems in using any of these resources. But there's a lot of fuel down there. So whilst in the long term we need to do something like we cannot continue to use fossil fuels to power the economy sorry about the phone ringing, that for the long term, because we will run out of the fossil fuels. And so we do need other sources of power. What we've really discovered over the last number of years is that we can't even afford to use all these fossil fuels now because of the effect on global warming that we have. So let's have a look a bit here, what we might do. So why are fossil fuels bad news? What is going on here? So I think here I should be able to click. So we have we take out the oil and the coal, we produce petrol, we produce diesel. And one of our problems when we run our engines is that we produce exhausts. And many of these exhausts we'll see quite a lot of problems. They produce particulates, we produce nitrogen oxides, we produce carbon dioxide. So running our cars has two, I would say, serious areas of issue. One is the local pollution that is being produced in the cities, sitting near a road, into our houses. These are the particulate materials, the nitrogen oxides that leads to ozone, making the atmosphere really unpleasant. And in some circumstances, you get smogs and really causes quite a serious problem for people breathing. And if you have pre-existing problems, young babies, older adults, where breathing in babies, the lung tubes in the lungs are very small. Adults can have, older people can have trouble with their lungs. This is quite a serious problem. The CO2 we've seen is a much longer problem. That's leading to the climate change issue. So we've got a dual problem here that turn out to have rather contrasting issues with them. So as we warm the atmosphere up with the CO2, we start melting the glaciers. The ones that are floating are not too much of a problem, but the stuff in Greenland, for example, which is on land, that ice, as it melts, leads directly to increase in the water, the sea level. So sea level is rising, and as the atmosphere and the earth warms, the water also expands, and that leads to sea level rising. And a lot of the population of the world lives actually very close to the water. And if we have significant sea level rise, we have significant problems of inundation of the land. And where are we all going to go? Where are we going to grow our crops? Not very easy. Strangely, in other areas, increase in the CO2, the global warming actually leads to some areas getting drier. But as we've also may have seen this year in Europe, and some parts in London, for example, recent, can lead to much more intense rainstorm and actually flooding. So we get every possible thing goes wrong. Basically, the weather gets much more extreme. These are all consequences of burning the fossil fuels, leading to global warming, leading to much more erratic weather. So carbon dioxide is the problem. But I could have perhaps advertised this talk as partially carbon dioxide friend or foe. We're going to look at a number of aspects of carbon dioxide here. So here's a measurement. This is a measurement, you may well have seen this picture before. is a set of measurements of the carbon dioxide level taken at the top of the volcanoes in Mauna Kea in Hawaii. And you can see the record that was started back in the 1960s. And you can see every year it goes up and down, up and down, up and down, and it's climbing. The up and down is because of the seasons. So when there's a lot of, it's warm and there's a lot of sunlight around in the Northern Hemisphere, all of the plants and trees grow nicely, take carbon dioxide out of the atmosphere. And then in the winter, they tend to be much less photosynthesis and much more respiration, and you get the CO2 level rising. So you can see the sort of modulation here that is possible from trees and other crops growing. So that's why, that also gives you an indication of why growing more trees will lead to consumption of CO2 and a reduction of the CO2 level in the atmosphere. But on the other hand, you can see the magnitude of these oscillations is quite small compared to the overall trend here and the rise from 320 parts per million in 1960 to well over 400 parts per million currently. What you might not have seen is the red line, which you can see is the same trend from the mid-1970s upwards without so much oscillation. That is actually the CO2 level measured in the atmosphere of Tasmania, so in the Southern Ocean, where there's actually, the seasons would be opposite. So you can see the oscillations that are there are in the opposite direction to the ones from the Northern Hemisphere, but overall there's less land and less variation in the activity of biological activity removing CO2 from the atmosphere. So there's much smaller oscillations there, at least according to the data I've seen here. But you see the trend is global. CO2 is well mixed in the atmosphere, and although there are some hemispheric differences, the overall trend is very clearly upwards. Now that's only since 1960. In fact, 1958, I chose the start date because that's my when I was born. So this is the rise in carbon dioxide since I was born. But it's something we'd like to know what happened in the past. And there are ways of inferring the carbon dioxide level in the past. One of the ways is to go and drill a big, nice core through the ice in Antarctica or Greenland and bring out the core, this ice core. And if you look carefully inside these ice cores, there's air pockets trapped in the ice. And if you carefully examine the air in there, you can see what the carbon dioxide level is. Now, that's not a terribly reliable way of doing it. When you can, it's great. But there are other ways, which I won't go into, that you can infer what the carbon dioxide level must have been in the past. And we can go back here to about 800,000 years before the present. And here you can see the graph of the CO2 levels go up and down. And a lot of this correlates with ice ages and advance and retreat of the ice going up and down here. But you see, over the last 800,000 years, the highest it ever reached was around 300 parts per million, which is about the level that we were starting at just before the 1950s. And then in this very small bit of the graph here, you can see that the CO2 level has risen up hugely just in the last few years. This whole bit here is the part of the last graph. So all these oscillations, not only in this whole region did the CO2 level never rise as high as it is now, it also didn't move up and down nearly as quickly as it has done in the last few years. So not only is it the level rising, but it's also the speed with which we're changing the environment at the moment, which means that it's going to be quite hard for anybody to adapt to the change. So why is this a problem? Well, what is the CO2 doing? Well, CO2 is a molecule we'll see that absorbs infrared radiation. I'll say a bit more about that in a moment. So we have the sun here that's producing a whole range of infrared, visible, ultraviolet radiation. And this comes in through the atmosphere. Now, some of this is absorbed by the atmosphere, but quite a lot of the visible light comes through and warms the Earth's surface. But the sun has a temperature of about 6,000 degrees Celsius, and that's why it's nice and yellow and we get a lot of visible light. The Earth warms up and it has to radiate back out the same amount of energy that came in, otherwise the Earth would just get hotter and hotter and hotter, which it's clearly loosely in equilibrium here. So the Earth warms up to radiate back out the heat as infrared radiation, because the Earth is at a much lower temperature than the sun, so the majority of the radiation goes out as infrared. So when there's no particular problem, not a huge amount of CO2 in the atmosphere, actually most of this infrared radiation escapes. Well, I should say most, but that's not entirely true, because or in fact not true at all. Water molecules, which are in the Earth's atmosphere, are also very significant global warming gases. If we didn't have any of the water vapor here, then the Earth would be so cold that it would be ice all the time, and that wouldn't be very good. So we do need some global warming due to the infrared absorption by gases in the atmosphere. We just need the right amount, not too much. So what is happening here is if the gases water and CO2 and methane all absorb some of the infrared radiation, and then they re-emit it. But when they re-emit it, they emit some back down to the planet and some out. So some still goes out, but in contrast to when those gases are not in the atmosphere, some comes back down again. And those greenhouse gases then act to re-warm the Earth. So one way of looking at it is that they provide a belt around the atmosphere that sends some of the infrared radiation back down, warming the planet. One of the consequences is that the atmosphere warms, the Earth warms, but actually the upper part of the atmosphere cools because no longer is as much of the infrared radiation coming to the upper part of the atmosphere. So the Earth's surface and the lower atmosphere warm and the upper atmosphere cools. Now, we've mentioned already the problems of global warming here and what they do to the environment. This global cooling that occurs in the stratosphere actually makes things like the ozone hole over the Antarctic worse. I don't have time in this lecture to talk about that, but the global warming aspect is only one side of what the carbon dioxide is doing. And the carbon dioxide and water vapor work together, because if the carbon dioxide in the atmosphere warms up the oceans a little bit, then more water vapor goes into the atmosphere, and then the water vapor and the CO2 warm the atmosphere. So we have a really concerted effect here. I would like to point out that the first observations that led to the understanding ultimately of the effect of CO2 in the atmosphere were actually made by an American woman, Eunice Foote, in 1856, largely ignored for many years, and Tyndall a few years later in England did a whole lot of work on this, and then Arrhenius in Sweden, and this has all led on to our full understanding of global warming. So we have kind of known about this for quite some time, but I don't think we appreciated all of the consequences of it until quite recently. So let's have a look at what these molecules are doing, or in particular CO2. So here is my carbon dioxide molecule. So it's a carbon atom here in the middle in black. Traditionally, we have the carbon atoms in black and oxygen atoms in red. And here was a double bond between the oxygen and the carbon. And this is a linear molecule. But the linear molecules are not, these molecules are not static, and they can actually vibrate. And there's a set of vibrations where they stretch, and some of them stretch together in and up as a symmetrical stretch, and some an asymmetric stretch. They can also, here's our water molecule, which I've mentioned is also another greenhouse gas. And here are the symmetric and asymmetric stretches of the water molecule. They can also, these molecules can also bend and here you see the bending of the CO2 and the bending of the water molecule. All of these vibrations occur in the infrared and some of these motions are very effective at absorbing infrared radiation. The infrared radiation promotes these vibrations and both bending and stretching vibrations. And that's why these gases will absorb the infrared radiation, absorb it in the atmosphere and re-radiate it back out to the ground. So here I'm just highlighting again that without the gases there, the radiation would escape out through to the out into space. But if we have then that's going out, but if we have the molecules in there, it comes back down again and we get the greenhouse effect. And that's where we get our heating from. And oops, I think I duplicated a few too many arrows here that we're sending off out into space. Now, it may not have escaped your notice. A few months ago, there was a serious set of pictures in discussions in the media, and here is the BBC that can never manage seeming to get in a headline headline a lowercase 2 for CO2, but there was a shortage of CO2. So here we have a problem that keeps coming up in lots of bits of environmental chemistry, that we have, the situation is that we have and too much CO2 generally, but apparently not enough CO2 when we need it. So it was going to be a serious problem of food and drink. We weren't going to have any food because there was no carbon dioxide. So what was going on here? How can we have so much being produced that it's a problem for global warming, and yet somehow we don't have enough CO2? Well, you might have also heard that this was linked to some of the fertilizer factories deciding it was too expensive to run in the summer, and they didn't need to make fertilizer at the moment because the farmers tend to put fertilizer down in the autumn and not necessarily in the late summer. This all has to do with the Haber process. The Haber process produces ammonia. It's a reaction of hydrogen and nitrogen, and it needs a lot of energy, and it's being used to produce millions of tons of ammonia each year, which are mainly combined to then make ammonium nitrate and others to make fertilizers. It's extremely energy intensive. The nitrogen bond is extremely difficult to break. You have to put a lot of energy in to make ammonia. And even with all the best catalysts we have in the world, we're nowhere near as good at making fixing nitrogen as the root nodules in some of the bean plants that we could grow. As a result, the energy consumption that comes actually from natural gas, and up to about 5% of the natural gas production is used to make ammonia. And that's a few percent of the world's energy supply. Now, you might want to wonder, what is methane being done, the natural gas? Why is that involved in a Haber process that needs to be making ammonia? And when I first looked at it, I thought, oh yes, it's just to heat things up. And then I realized and looked up, it's a lot more interesting than that, because methane is here being used, the Haber Bosch process, taken here from Wikipedia. Actually, it's quite a nice process, and this diagram is really quite good. I won't go too much in detail here, but the idea is that somewhere in the middle here, the entrance here, methane and some water are put in, and some air comes in with oxygen and nitrogen. The methane, it is arranged that we burn the methane to basically make, instead of we burning it all the way to make CO2 and water, which is what would happen normally when we burn methane or burn any of these sort of hydrocarbons, we actually do it in such a way that we get a combination of hydrogen and carbon dioxide. And this is why this was such a convenient process to then say, oh, while making all this carbon dioxide, it's all in the gas, it's all quite simple, we know exactly what's going on here. So we can funnel off a huge amount of the CO2, which we deliver to the food industry for putting in beer, putting in fizzy drinks, euthanizing animals, and so on. And it was a very key component to the food industry, as well as a number of other industries. And it's because of the huge consumption of the natural gas here, this is a very convenient way of making some initially carbon monoxide and hydrogen, and then you go on to make CO2. And the hydrogen then goes on to react with nitrogen, with more heat going in and ending up making the ammonia to make the fertilizers. So when they decided the cost of the methane, the natural gas was too high, they stopped this process, which meant they didn't make the fertilizer, but that's the immediate consequences of that. But the consequences of not making the CO2 were significant. So that's an interesting idea, because it shows you that we can turn our methane into hydrogen, and that could be a source of hydrogen that we could use in cars, hydrogen-driven cars, or other reactions to other ways of powering fuels instead of hydrocarbons. We could use hydrogen. When that burns, you make water. So you think that would lead to much less pollution if we had a hydrogen car. The problem is it made CO2, and we don't want to make the CO2, and we want to, but if we do that, we could trap the CO2. So there's quite a lot of work going on to trapping CO2 and putting it away in a reservoir. So this is the basic reaction here, that we have methane and water to make carbon monoxide and hydrogen. This positive sign here means that we have to put a lot of energy in. There's another way of making hydrogen and actually getting carbon monoxide, which again we could do something with, which is actually from coal, essentially carbon and water. This is a route that's been used in the past to make hydrogen. But it still leaves you with carbon monoxide and ultimately carbon dioxide, which we'd have to trap somehow and use. There is work going on about a different reaction that would take methane and sort of take it apart to its carbon, solid carbon and hydrogen. And we might be able to bury the solid carbon a lot more readily than we can bury the carbon dioxide. It's easier to deal with solids. And so there's work going on looking at these quite fundamental reactions, trying to understand whether we could use those and make them efficient to provide different sources, in particular of hydrogen to power the economy. We'll look at alternative fuels in a moment. And one of the reasons why I wanted to mention that is that apparently we've just, or some UK companies have just signed a deal to get green hydrogen. So that is hydrogen that does not give you CO2, but apparently we're importing it from Australia. So I don't quite know how that works with the most reasonable way of running the global economy to import hydrogen so far from halfway around the world. And I don't quite know what process they will be using in Australia to ensure that it doesn't produce the CO2, but maybe they'll use sunlight to produce electricity and actually use an electrochemical process to split water. We'll see. So here, just then a reminder of the harmful effects of CO2 emission here, particularly melting of glaciers, lack therefore of water supply in some region, increased water and flooding in other areas, and decreased rainfall due to higher temperatures in others. So basically making quite a lot of the world much less inhabitable, less suitable for growing crops. I apologize, I don't know why this is not running the poll. There doesn't seem to be much I can do about this at the moment. I think, I'm sorry, we're going to have to go without the polling here. I don't know why it worked for the first one, but not these ones. I think it's safer. We'll just have to ignore that at the moment. Really apologize for that. So one of the suggestions, and this is what the poll would have been about, is to, you've heard about alternative fuels that we could use, one of which is biodiesel. So this is looking at the alternative actual fuels, actually saying, well, we've already grown these crops. Some parts of the things that we've grown we don't eat. So like we use straw for many other things in the ecological cycle, we could maybe turn some of these parts of the crops into other fuels. Maybe there's other oils and things that we've got that come from biological origin. Maybe we can process them in a way that will give us a fuel that we can put in diesel cars. An alternative is to actually say, well, let's make the CO2, but maybe we can bury it. So if we've got places where we've got reservoirs underground, where we take an oil out, like over here, then we can take out the methane gas, burn it in the power station to make electricity. There's a clearly localized source of CO2. We haven't let it out into the atmosphere, and we can trap it and bury it back in the areas. And this is called carbon capture and storage. The question is, can we really believe that it will stay there for long enough? Alternative sources completely would be to go ultimately to fusion. Fusion, it would be an almost unlimited source, but as you're probably aware, this is really quite tricky. And at the moment, whilst we're making progress, it's still going to be many years off, we think, until we actually do manage to create fusion. If we can create this great source of electricity, then we can actually power many more things, and we could use that electricity to create, for example, hydrogen for places where we do need to carry fuel with us. It's hard to see how we're going to have an electric powered rocket, for example, and electric powered trains, that's fine. Big trucks and things, that's still going to be a problem to see if we could really run them all from an electrical source. Other side of things is to be just far more efficient here about our use of electricity, and changing the light bulbs to modern LED light bulbs has reduced the amount and consumption of electricity significantly for producing the same amount of lighting. So as well as working out how to produce electricity in an efficient manner and not produce CO2, actually just using less is going to be a significant thing to do as well. These areas of storing CO2 and creating new alternatives, batteries and so on, is something that's active in Southampton. And with recently, some of the Southampton researchers have spun out a company to actually take CO2 and with additional energy, convert it into useful polymer materials, and therefore actually make the whole cycle there of research of use of carbon-based materials much more useful. I mentioned creating hydrogen and actually making more efficient use of fuels that are less polluting. And one way of doing that is to use the hydrogen and recombine it with oxygen, for example, to make a fuel cell. And we're working on that to make some of these things more important. But if we have all our renewable sources of energy, one of the things we need to do is to store that energy, because we, for example, solar energy is only available during the daytime, so we need more efficient batteries. And this is again area of active research in Southampton and in other parts of the world, of course, as well. Now, so these biofuels, so let's just look at that. So the idea is you take a renewable source, so it's basically taking the carbon dioxide from the atmosphere. Solar energy comes in, that means we get some crops, we might even use some of it to eat. But the rest we create biodiesel from, usually by some sort of fermentation process. That gives our renewable fuel. That means we take it into existing cars and other technologies, which will burn it and produce the CO2, but the CO2 will be captured by the trees. It's kind of a bit ridiculous to be thinking about diluting all that CO2 in the atmosphere and then asking the efficiency of trees to trap it back down again. But clearly this is better than digging up the fossil fuels and bringing out carbon that has been buried for millions of years back into the atmosphere. So that's the basics of the biofuel. If you can grow your fuel, then it's carbon dioxide neutral. Some of the fats and things, for example, if we have oil, so we take some of things like sunflower seeds, whatever that you might use for vegetable oil, for example, use that for cooking. McDonald's uses it in making its burgers and takes all the output from there and turns that into biodiesel. So the idea here is that you actually work on your triglyceride. That is the typical spun pumps of the fats that are in some of the oils. Other oils are longer chain hydrocarbons, and split these things up to make slightly smaller compounds, which these esters which form the basis of the biodiesel. So this is not the simple hydrocarbon fuel we're used to in terms of petrol, but it turns out diesel engines can be quite efficient at burning that. So that's where we can cycle that all the way around. Perhaps a slightly more ingenious thing that's been in use for many years, for example, in Brazil, and is in use now, is that you can actually mix ethanol, so alcohol, in with petrol engines, and with very minor modifications, if anything at all, that works very well in most cars. So in up to 30% of the fuel, petrol in Brazil is ethanol, but most cars will actually run on up to 10%. And you might have seen in the press very recently that the fuel in the UK has changed from, I think, about 5% ethanol to 10% ethanol, but almost all modern cars are capable of burning that without a problem. I think if you have an older car, you have to go and seek some advice about how to deal with the new fuel. But that's what the E10 fuel actually means. So many countries are now starting to put significant amounts of ethanol in the fuel, in the petrol, because that is a regenerated part. It comes from organic matter that we grow. And I think the next slide says, basically, we make the ethanol by fermentation. So exactly the same way that it's made for making beer and wine. We have the yeast, and that generates ethanol. It does generate some carbon dioxide at that point, but of course, this is carbon dioxide that was originally trapped down to make the plant material that we're actually fermenting. So that's it doesn't really upset this sort of zero cycle going round. And this can be done on an industrial scale. So we can make a huge amount of ethanol is being made. And that goes in the fuel, and that saves us a little bit in terms of the amount of carbon dioxide. Now, unfortunately, I was going to have a poll here on how many liters of water in an Olympic swimming pool, but I guess you just have to see the range of answers that came last time. I again apologize for this. But Olympic swimming pools are pretty full of water. It's a lot of water, but not that's still small compared to the amount of bioethanol that's being produced. But if I gave the comparison of the amount of petrol that's being made, you'd see that we're still only making a very small dent in the contributions of these biofuels to the total amount. So the Olympic swimming pool contains about 2.5 million liters of water, and we're making 60 billion liters of fuel, but we must be using, it's actually billion liters of fuel in ethanol, but we must be making orders of magnitude more of petrol of that. So yes, 500 billion liters of gasoline every year being used in the USA. So it's a contribution, but it's a small contribution. Now, the point about this was to ask that biofuels, they have their problems. It's not completely a simple solution. Could we run everything off biofuels? Well, are they really carbon neutral? Well, I think that really depends upon the efficiencies of the process. And there is a problem. If you take out an existing forest, a mature forest that's been quite good at capturing carbon and carbon down into the soil to grow a modern crop for the biofuels, that can often lead to a net gain in carbon dioxide coming out into the atmosphere because of the disruption to the mature forest that was there. So that's not good. There you then have ecological consequences because you've removed an area where, for example, these animals might live. So you've changed the environment, and that reduces our biodiversity. The efficiency of engines may be much worse, so we end up burning more fuel. Now that's something that we can probably do something about, but we do need to know how efficiently do engines run on biofuels, and some engines won't and others might. So that's the difference between running on biodiesel and ethanol. So that's a really big consequence. And are the emissions from biofuels the same, or are we going to cause more or potentially less problem with atmospheric pollution in the environment if we use biofuels? So we can't just simply swap one thing for another and assume that it will get better. We do need to make a lot of measurements, and these are the sort of things that the chemists can measure. So let me indicate here one of the sort of fundamental problems. I think you're probably aware of the big interesting disaster that befell Volkswagen for cheating on its efficiency measurements for diesel engines that have led to very fewer people buying diesels because they turned out not to be as efficient, it was thought, as they were. Probably really unfair in the long run. Diesel engines are more efficient and longer lived than petrol engines. Now, one of the things that goes on here is that if you want a more efficient engine. Why do we want a more efficient engine? Well, a more efficient engine means we burn less fuel. To get a more efficient engine, you fundamentally need a higher temperature in the engine. It's basically the efficiency of an engine, the chemical engineers will tell you, depends on the highest temperature in the engine versus the lowest temperature in, if you like, the radiator. So the higher temperature means we produce less carbon dioxide per kilometer driven, so that's more efficient. So that's great for the future. But the higher the temperature in the engine, this gets more and more like that Haber Bosch process. The higher the temperature, the easier it is to get the nitrogen to react, and in fact react with the oxygen to form the nitrogen oxides. So that the more efficient I've made this engine, the better it is at giving rise to air pollution. The nitrogen oxides leads to all sorts of problems, and it's not something we really want. So we've used in petrol engines catalytic converters, and it reduced the NO2, reduces it back to nitrogen. But one of the problems that we get from diesel engines, they form many more particulates, which are really not good for us at all, but they also block the traditional catalytic converters. So this is the sort of, that was one of the fundamental difficulties with the diesel engines, is you needed to do more to reduce the particulates and work out how to put a catalytic converter on them, which the petrol engines already had. But fundamentally, the tension here is the more efficient we make the engine, which gives us less CO2 for the miles we've driven, the more air pollution locally we get. One of the people in this area put it, it's a balance between killing people now with air pollution versus killing them in the future due to global warming. So we have some real conundrums here that we need to find different ways of solving. So I hope that's illustrated some of the issues around some of the chemistry in the environment and some of the mixed messaging that we get around CO2, some of the difficulties we have. We need it, but we don't. It's a real difficulty. But let's look at some of the other areas in which the chemistry can help us, some of the materials. And again, I really apologize for not having this. But all sorts of really interesting forms of carbon have come to the fore in the last few decades. Carbon graphene, buckmaster fullerene, carbon-60, graphene, these layers, carbon nanotubes, all sorts of really interesting things that we think could revolutionize many devices. There are graphene transistors that could well graphene, and then carbon nanotube transistors. Graphene is a wonderful material. It's 1 atom thick, and you can get films made out of it. It's a pretty amazing sort of thing that you can think of. So these were all novel bits of chemistry. That's a layer of graphene there. It was originally found by taking graphite and using a piece of sellotape to take off 1 atom layer at a time. So you think of a material robust enough here, it's 1 atom thick, and you can support it and put things on it. It's an amazing material. So it's the thinnest and strongest substance known to science. It conducts electricity really well and heat better than anything else. Water vapor doesn't pass, can pass through, but other alcohols, other compounds don't. So you can actually to purify water. It's optically transparent, so you can use it. It's also fairly transparent to electrons, so you can use it in electron microscopes. So huge number of potential applications. They're developing a bit slowly, to my mind, but nonetheless, really amazing factors that you can get from these new materials that have new properties. And in fact, the latest thing is to put 1 or 2 layers on top of each other and slightly twist one layer with respect to put an angle of a couple of degrees between them, and it turns out that makes a superconductor. So there's a lot of chemistry and physics here that we don't really fully understand yet. We have a problem, I'm sure you're all well aware, with plastic bags, that we have too much plastic around. But plastic is an amazingly useful material, but maybe there are ways that we can make the plastic much more biodegradable in a way that means that it really will disappear from the environment properly. And here's an example, you can look at the link there, of biodegradable polymers. So really interesting things. Now, we've got to make sure they really are biodegradable, not just fall apart into lots of small bits, which get all through the food system. There's a lot too much plastic in the food system already. Another area that's chemistry traditionally makes a huge impact on and has been very relevant recently. Well, that would have been asking you a question about what this particular compound that comes from a chemical found in willow bark, and this is aspirin. Aspirin used to be the go-to medicine for a headache. It's now people who have perhaps increased risk of heart attacks will take it. It's got a number of uses, perhaps because of some of the side effects of aspirin itself, less used as a painkiller now, but nonetheless was one of the first clearly defined sort of modern medicines that derives from natural products. But we've gone on to generate many more things. So the artemisinin is an anti-malarial compound developed by some old Chinese medicine, and understanding that and isolating the really important active ingredient. That's been really important at treating malaria. Unfortunately, some of the malaria parasites are gaining some resistance to artemisinin, so have to be quite, these bugs evolve very rapidly and will try and find a way of getting round anything that you put in. Just needs one random mutation for a particular bug to be able to survive even in the presence of artemisinin, and you start to generate a resistant population. Taxol is an anti-cancer agent, because these are really quite complicated molecules. When it comes to making them, some of these are still made and isolated largely from the biological systems and tailored afterwards by traditional chemistry. And vancomycin is another basis for antibiotic. These are really quite complicated molecules, which means making them and handling them and delivering them to the right part of your body is really quite complicated. So there's finding molecules and then making molecules and then delivering these molecules to you as a drug. All these aspects are quite important and different. The classic, of course, is the unexpected discovery of penicillin. And this is the structure of penicillin. It was a very novel compound in its time, and penicillin has this antibacterial activity. And it works by stopping the bacteria from building and interlinking their strong cell walls. So bacteria have ways of building up these interlocked polymeric walls, which protect them. If you can stop them and break this, the sort of bacteria, the middle of it bursts out, and you basically kill the bacteria. So this is one of the ways that the penicillin works. And it works by blocking, this bit of the molecule blocks the way in which the cell wall should form. And as a result, just prevents the cell wall linking up properly. And the cell wall is either broken or fails to form, and the bacteria is killed off. Now, unfortunately, of course, various versions of these bacteria also worked out, randomly managed to produce some variations of enzymes that in their body, that variations of enzymes that are already there, that actually dispose, they hydrolyze it. So they take the penicillin, it's an amide, and they basically could hydrolyze it, and the hydrolyzed form is no longer active. So the resistance mechanism is to basically create some enzyme that destroys this antibacterial agent. And as a result, the bacteria could survive. So the chemists come along and looked at that and started to develop variations on, okay, this is methicillin, so variations on the penicillin molecule that were more resistant to being hydrolyzed by the enzyme. And of course, then other mutations might occur that will try and find other ways of disposing and getting rid of the antibiotic agents. And so it becomes a war between the medicinal chemists and the bacteria. I thought I would mention a couple of things that are very recent. So many of you will be aware, some of you may already had a vaccination against COVID-19. I hope if it's available to you, you've taken it, take advantage of this. And that helps your immune system develop systems to attack the virus when it comes along. The most recent advance has been actually some antiviral drugs based around some of the drugs developed for HIV that actually interfere with the ability of the virus in you to be able to replicate. So this isn't the priming the immune system, this is actually going in and preventing the virus from replicating. And these are the compounds that have just been released by Merck and Pfizer that you would take once you were already ill to reduce the impact of the disease on you. So I think this is, again, the medicinal chemists looking at the mechanism by which the virus replicates and seeing whether they can create smallish molecules here that will go in and block that and prevent the replication enzyme from running inside your cells and producing more of the virus. So this, again, a very important impact of the medicinal chemists. But it's not all sort of fighting medicine. There's some very interesting things going on. So you may all be addicted to having nice chocolates and sugar and all the rest of it. Well, here is a compound that is 200 to 300,000 times as sweet as sucrose. So you don't need very much of this to sweeten your tea. It's not likely to replace these sweeteners at this stage because it's probably not worth actually developing all checking out the toxicities and so on. But just shows you again that it is possible to design molecules that trigger, in this case, the sweet sensors in your tongue, hugely more than normal sugar would actually do. So all sorts of interesting things we can get up to as chemists, making these compounds. And many of my colleagues are busily working at this, doing synthetic biology, so chemistry and biology combined, to look for treatments with cancer, therapeutics, innovative dyes, markers to be able to look inside your body. So whether this is an optical or magnetic resonance techniques to tag things in your body to make them show up more readily when you're being scanned, if you have to go to hospital and be scanned to see things. These are all activities that are going on in Southampton and all things that our degree contributes to and trains our students to be interested in and able to take forward either in research or in industrial environments. Our courses have a focus on sustainability, chemical sustainability, as well as sustainably doing our teaching as well and running the university in a sustainable manner. And of course, I therefore encourage any of you might use the option to study abroad, to go abroad by train. It depends where you go, of course, whether that's possible. And some new courses that we've started over the last year or two. We now are running a course in chemical engineering, so bringing chemistry and engineering together, and also using many more digital and computational methods to drive chemistry. So the intersection, if you like, of chemistry and computer science here. And we have some nice new labs, which we would be delighted to show you. Now it's getting a little easier if the COVID rate doesn't rise too much to invite you in to have a look at our labs. So, you know, if you want to know anything more about studying chemistry, do talk to it, come and give us a call, contact us, and we can tell you more about what goes on in our chemistry courses. So again, apologize, you can't make a poll, but I'm sure you would all have polled this way that you think scientists will solve, best place to solve the problems in the world. And hopefully we can inform the politicians. Over the last year, they've listened a little bit more to the scientists and the medics about what they should be doing, but perhaps I would say still not enough. Now, I think that if I asked you all, do you think we'll solve the problems in time? You'll probably get a mixed answer here. And I think I would go for the I don't know, but I certainly, now that poll worked. Okay, so let's see. Let's see if I can get you at least to answer one poll, hit one more poll, and see what you think about whether or not we'll solve these problems in time. I'm assuming it'll be the scientists, but it's actually everybody. It's society, government, so on. I think I now understand what I should have done in the previous polls, and so I'm sorry about that, but let's at least do this one. How are we doing? Okay, I think we're nearly there. Oh, people managing to get into the system. Okay, I think we'll click here and see. Okay, so I think you're aligned with me that we don't really know. Some of you are very pessimistic. There's 10% of you, but I think, yes, I don't know, but I hope so. And I agree with you with that I definitely hope so. So let's go on here. And my view on that is, this is a cartoon from the New Yorker of these two dinosaurs. All I'm saying now is that now is the time to develop the technology to deflect an asteroid. I feel we're in that sort of situation. We know what the problems are that we're facing. We even kind of know what our solutions are, where the direction they have to go in, but we know how difficult it is, and we really need to do something about it. And a lot of that is going to come down to your generation, but we hopefully can provide you with many of the skills you're going to need to be able to help solve the problems here. So thank you very much for listening. It's unusual to, even to this, given the last 18 months, it's still a bit unusual to give a schools talk in this manner and not be able to see you all. And this was another New Yorker cartoon that comes from a time before the COVID-related Teams, Zoom, whatever life that we live in, where he's saying no electronic communication superhighway, no matter how vast and sophisticated, will ever replace the art of the schmooze. Well, that may be why they're doing the meeting in Glasgow at the moment, but I think we have to learn how to schmooze over the internet to reach everybody in a sustainable manner. That being said, of course, the internet itself is a huge consumer of energy, and we do need to worry about that in the long term as well.